additional developments they wanted to take account, or David wanted to take into account, was the dependence of temperature on the wax conductivity. And so this additional detail was desirable to be added into the model that they'd previously considered, due to the feature that the conductivity of a material near to its melting point can change quite drastically. And so this is a key feature of the original model, and it's a key feature we'll be sort of investigating here. Now, as to why we're investigating this, well, the best thing I can do probably is show you a picture. So this is Tulsa University's Paraffin Deposition Project's webpage. I can get away with showing you this. Now, what you can see here is the cross-section of a pipeline. So this is an experimental setup. And you can see the pipe, you know, is a grey sort of colour, but in the majority of the bottom of the pipe here, you've got this orangey deposit. And this is the paraffinic wax deposit that you get when you transport heated oil through pipelines which have an external cooling jacket surrounding them. And the reason that this is of interest to industry is that as this wax layer builds up, what in principle this does is minimize or make smaller the cross-sectional area of the pipe where you can actually produce flow oil through. And so in extreme cases, this can actually compromise the efficiency of the oil pipelines. So there's interest within industry to understand this physical process. And as you can see here, actually, there's a whole department at the university set up to investigate this. And this investigations will also be taking place within industry as well, to understand this phenomenon. Now, in terms of actually rectifying what happens with this particular phenomenon, so if you have a pipeline where this paraffinic wax deposit has built up on the interior of the pipe wall, the only cleaning mechanism that's available to industry at present is a so-called pigging operation. And this is where a mechanical sort of device will be inserted into the pipeline, and it will scrape off the wax that is attached to the pipe wall. Now, an important feature of these pigging operations to clean the pipelines is, one, you have to shut the pipeline down to actually conduct one of these operations. So whenever you're cleaning the pipelines, you can't flow oil through them. So that is a substantial problem. The second problem is it's quite difficult, even with these devices, to actually scrape this wax deposit from the wall. These devices are liable to break down, and with every moment that the pipelines are closed, the industries who are operating them will be losing money. So it's of interest to the industrial, the industry concerned with moving heated oil through pipelines in certain types of environments. It's important to them to understand how this wax flow builds up and how regularly they need to inspect pipelines for this particular buildup, and also essentially accommodate for it. So accommodate for how frequently they need to clean these things. So roughly speaking, that's the physical phenomena. So you've got hot oil in a pipeline, and it is flowing transversely to the pipe, or in line with the pipe. And in these particular cases, the pipes are surrounded by a coolant jacket. Now, in the experimental setups, this is an exterior pipe with water in it, which is kept at a certain temperature. But in applications or in reality, this will be the sea. So usually we're talking here about pipes carrying heated oil, which are under the sea. Sorry, was there a question? I'm not sure. I can't see anything, so I'll assume there wasn't. Yeah, so these what we're interested in here are pipes carrying heated oil which are carrying oil underneath the sea. So they are pipes that are surrounded by a coolant, but are carrying heated oil. Now, yeah, and I suppose now at this point we can go to the actual slides. Zoom. The thing's always in the way of half the slides. Let's go over here. There we go. Okay. Okay. So the assumptions that we'll first discuss modeling assumptions related to this physical process. And these are as follows. So we assume that we are going to have a pipe of radius r, or capital R. And additionally, we will assume that the height, or the stable equilibrium height of our wax buildup is substantially less than r. Of course, if the wax built up to the radius of the pipe in uniformly across all the things, you wouldn't have any flow in the pipe anymore. It would just be solid wax. So we assume that the height of our wax buildup is substantially less than the pipe radius. And at least initially, this is a reasonable assumption. Over long periods of time, depending on the situations, if the pipes haven't been cleaned, this may not apply. But in many applications, this is the case. Additionally, we're going to consider, for the sake of simplicity, a long, straight cross-section of pipe that is far enough away from bends and exit-entry effects of the oil entering or exiting the pipe. That's transversely to the pipe, or perpendicular to the pipe wall. So this assumption is made, or the third assumption here is made so that we can essentially consider the buildup of wax to be uniform along this section of the pipe. So we only really need to consider the wax buildup in one cross section of the pipe. So we don't need to consider the whole pipe length. We can just consider a cross-sectional length. And so this is point 4, that here, because of this assumption 3, we can assume that H is independent of the axial distance along the pipe. In other words, we're assuming that H builds up uniformly away from the wall of the pipe. Now, the fifth point here, we assume, and so this point is quite important. So we assume that we have oil wax mixture that's flowing through our pipe, and we assume that our pipe is surrounded by an exterior coolant jacket. Now, in reality, this would be the sea, but in experiments, this would be an outer pipe with a constant temperature water maintained in it. And we denote the temperature of the oil wax mixture to be T subscript O, and the temperature of the coolant to be T subscript C. Additionally, well, we're interested in the buildup of the height of the wax layer, and the mechanism we're going to propose is primarily a thermal phase change mechanism. And so that means we need to denote temperatures for all of the components in our model. And so that includes the pipe wall. So we denote the temperature of the pipe wall to be Tp. Now, we also denote the temperature in the solid wax layer. So that is the solid wax layer on the boundary of, or between the pipe and the hot fluid flow. We denote that to be T. And we denote the temperature at which wax forms. That is the solidification temperature at which the wax converts from liquid state to solid state to be TH. Now, some important sort of fundamental points about these temperatures here. For the phenomena we're discussing to occur at all, we need the temperature in the oil wax mixture, to be above TH. That is the solidification temperature for the wax. Otherwise, the wax will be solid. We also need the temperature of the coolant, that is the temperature outside the pipe, to be less than the temperature of the wax solidification, that is TH. So we have T0, or TO, sorry, is greater than TH, and TH is greater than TC. And so here we're assuming the temperature of the oil and the temperature of the coolant are constant. And this is reasonable to assume. And for any particular oil wax mixture, we could in principle find TH based on chemical properties of the paraffinic wax we are considering. The things that are unknown at this point are TP, that is the temperature in the pipe wall, and T, that is the temperature in the solid wax layer. And importantly, the thing we want to know about, H, this is also an unknown. So the main thing we really want to know here is H. But to find this, we'll also need to find the temperature in the pipe wall and the temperature in the solid wax layer as well. Now, these are just bullet points. A schematic diagram of the problem is perhaps more helpful. And so what we have here is so if we consider the x-axis to be essentially a line pointing from the wall of the pipe into the middle of the pipe. And so this x would be a line in the x-axis here is a line in the cross-section of the pipe. So where x equals 0, we have the interior pipe wall. So this is the interior part of the pipe wall. And we say the thickness of the pipe wall is d subscript p. Additionally, in this case, we're considering the experimental setup, and we consider the thickness of the coolant jacket here surrounding the pipe to be d subscript c. Okay, and these are the outer parts. And the temperature here again in the coolant jacket is Tc. The temperature in the pipe wall is Tp, which is at this point unprescribed. Additionally, between x equals 0 and x equals h, we have our solid wax layer. And this has a temperature profile T, which is to be determined, or is still unprescribed. And at x equals h, we have our upper part of our solid wax layer. And so importantly, at x equals h, this is where the liquid wax in the oil wax fluid flow is solidifying. So this is where you've got temperature TH, or the temperature is going to be TH at the point where wax is turning from liquid into solid. And at the top part, we have our oil wax fluid flow, which is just a fluid flow going to the right. I'll stress here again that we're not considering really the fluid mechanic effects of the oil wax fluid flow in this particular case. It's more to do with the model we're proposing is more to do with a thermodynamic effect of the wax, the liquid wax in the fluid flow solidifying, and that's the main feature of this model. And we'll find that actually this relatively simple model does seem to describe a decent number of the experimental observations, certainly qualitatively, and with more details, hopefully quantitatively. But we'll get to that later in the presentation. Okay, so let's consider first, well, going back. So what we need to do first, we've assumed that the temperature in the coolant is constant. We've assumed that the temperature in the oil wax mixture is constant. And we, in principle, know what TH is for a particular wax. We now need to find T and TP and H. Okay, so to start with, we'll look at the temperature in the pipe wall. So we don't do anything too non-standard here. We just use Fourier's law, that is, to describe the movement of heat within a body. And this yields the heat equation for the pipe wall. So the temperature in the pipe wall, Tp, it satisfies the linear heat equation. Now here, and so of course this heat equation is satisfied for x in the right region. So the pipe wall, recall, is between x equals 0 and x equals to minus dp. And this time is for t greater than 0. So this is where we would solve this PDE. Now, the parameters in this particular PDE are as follows. So we have Kp, which is the conductivity of the pipe wall. We have Cp, which is the specific heat capacity of the pipe wall. And we have ρP, which is the density of the pipe wall. And so this is a relatively standard approximation for how heat will evolve within a pipe wall. Now, if your pipe wall is sufficiently thin, so that's this case, we've said sufficiently thin means that the dP, or the thickness of the pipe wall squared, is substantially less than Kp times Ts divided by Cp ρP. Now, Ts here is a time scale for wax layer formation, which we haven't defined yet, but we will define when we non-dimensionalize the problem. So I will introduce this term later, but what I will say is, if your pipe wall is sufficiently thin, which in applications in terms of this right-hand side here, it typically is, if this is the case, then you can assume that Tp is in a quasi-steady state. So namely, instead of your heat equation here, you just have a time-independent version of this equation. In other words, that the temperature profile P, the second derivative with respect to x, is actually equal to 0. It's not dependent on time, and that this is still satisfied in the pipe wall region. Now, that's just a PDE, okay? And this is a second order PDE in one variable. Now, this second order PDE is quite simple to solve, right? And it's just got a general solution, which is, an affine function, ax plus b, where a and b are undetermined constants, or to be determined constants. And to determine these constants from the physical model, we need to consider boundary conditions. So the boundary conditions we apply, well, the first boundary condition we apply it at the boundary between the pipe wall and the coolant jacket. And what we say here is that the heat flux across that boundary between the coolant jacket and the pipe wall is maintained. So the amount of heat going out of the hot pipe is comparable to the amount of heat gained by the coolant jacket. And so that's, roughly speaking, what this first boundary condition means. Now, here we have two more boundary conditions that we impose at the inner pipe wall at x equals 0. Now, the first of these is to do with it's to do with continuity of the flux of heat across the boundary. So this says the amount of heat going into the solid wax layer is balanced against the amount of heat going out of the solid wax mixture into the pipe. Additionally, though, we prescribe another boundary condition, a third boundary condition, which says that the temperature is continuous from the pipe into the solid wax layer. So we don't necessarily expect that the temperature is continuous from the pipe into the coolant jacket, but we do prescribe that the temperature is continuous when we go from the wax layer into the pipe. Now you will notice here, so a couple of important parameters here. So Kp is the conductivity of the pipe. Kc is the conductivity of the coolant fluid. Now the Nusselt Nu here is the Nusselt number. Well, Nu subscript c is the Nusselt number of the coolant or the fluid. And so roughly speaking, this is determined by the amount of energy you need to move heat around via a convective process divided by the amount of heat required to move, the amount of energy required to move heat around via a conductive process. So the Nusselt number is sort of, is picking out the ratio of how energy is transmitted via convective processes over conductive processes. And so that's roughly speaking what the Nusselt number is related to here. And that is, in principle, all of the terms here. Now, notably, we've assumed here that all these constants so far, or all these physical terms are constants. But at this point, we've now introduced that the conductivity of the wax, that is Kw, we're supposing that this is actually dependent on the temperature of the wax. And so this is the key feature in this model that we wanted to introduce. So yeah, where we consider that the conductivity of the solid wax in principle should be taken into account for this particular problem, because the conductivity can change quite a bit around the wax solidification temperature. Now, just going back to this, so this is our formulation for our temperature in the pipe wall. So we have 1 PDE in equation 1.1 and 3 boundary conditions. Now, that doesn't quite add up because we've only got a second order PDE and 3 boundary conditions. Now, what you can do here actually is, because the PDE is quite simple, you can essentially solve for 2 of the boundary conditions and then leave the third one unprescribed. And so that's what we're going to do for now. So the solution to the PDE in 1.1 and the boundary conditions in 1.2 and 1.4, if we solve this boundary value problem and temporarily ignore 1.3, we get that the temperature profile in the pipe wall is equal to this particular quantity, where of course we've got an undetermined quantity, capital T here, which is our temperature of the wax at the boundary, or at the temperature of the wax next to the pipe wall. And so, yeah, the temperature in the pipe wall is dependent on many things, but it's dependent on this yet to be determined quantity, which is the temperature of the solid wax at the boundary of the pipe wall. And so what we can then do is say, instead of considering condition 1.3 in the pipe wall as a boundary value problem to determine the temperature of the pipe, what this feeds into is a boundary condition for the temperature T in the solid wax layer. So this additional boundary condition actually gives us now a new boundary condition for the temperature in the solid wax layer. And I'll say, if all the modeling is perhaps too much, don't worry. At some point, everything will be non-dimensional, and all these large constants and mixed constants will be gone, and we'll be left with a much simpler problem. But I felt it was meaningful to take you through the modeling of this physical process first. So now we've covered the temperature profile in the pipe wall. Of course, we still need to, and that will be determined once we know what the temperature profile is in the solid wax layer. So again, if we want to model now, so now we'll model the temperature profile in the solid wax layer. Now again, we can use Fourier's law to define a heat equation for the evolution of the heat profile within the solid wax layer. And it's via the same mechanism as before. The only difference here is, instead of having a constant conductivity for the wax, we now have a non-constant conductivity for the wax. We've still got our density and specific heat capacity for the wax here, which we do assume are constant. One wouldn't necessarily have to, and they could feed into this nonlinear term here, but it's not something we've done at this point. Now, there's a substantial difference between this particular partial differential equation and the linear partial differential equation for the temperature in the pipe wall. So this partial differential equation here, it would have had an equation number next to it, but it's too wide, so I couldn't fit it on the slide. This now is a quasi-linear parabolic partial differential equation. I suppose the parabolic part I should be slightly careful about because we haven't said what this conductivity function of T looks like yet, but it will end up being a quasi-linear parabolic partial differential equation. And this, of course, holds for all values of x that are between the pipe wall. So when x is equal to 0, you are at the interior of the pipe wall. And this holds up to h of t, which is the top, or h of t is the top of your wax layer, solid wax layer. Now, again, to solve the, to find a temperature profile here, we need to formulate boundary conditions for that resemble our physical process. So at the pipe wall, so that is at the boundary at x equals 0 between the solid wax layer and the pipe wall, we just have the equation generated from our temperature for the pipe wall. So this is just the boundary condition that we find from solving our problem for solving our temperature profile problem within the pipe wall. Additionally, we need to prescribe 2 further boundary conditions here. Now, the first of these makes physical sense quite clearly, which is that the temperature of the solid wax layer at the top of the wax layer, that is where the wax is solidifying, or it's turning from liquid to solid, we prescribe the temperature of the solid wax layer to be precisely TH at this location. So this is the temperature. So the temperature at which wax solidifies is the temperature T at the top of the wax layer. Additionally, we need a sort of conservation of heat energy term at this upper layer. And so this third boundary condition here, this tells us that the amount of heat required to create some solid wax is balanced against the amount of, or the balanced against the flux of the amount of energy coming into the solid wax layer from the hot oil. So this is sort of a balance of creation of mass against heat flux coming in from the hot oil into the solid wax layer. And that's what this third boundary condition gives us. Now, here again, rho W and CW are just the density of the solid wax and the specific heat capacity of the solid wax. And capital HW is just the latent heat required for the solid wax, which is the energy required to keep it essentially in that state, informally. And NU is the Nusselt number for the oil. So we have the Nusselt number for the coolant, but NU here we just denote as, so NU here, I should say, is just the Nusselt number for the oil. So we have Nusselt numbers for the oil wax mixture here in NU, and we have Nusselt numbers for the coolant jacket or the coolant fluid outside. And so this will give us what we need for our boundary value problem. Now, just to recall again here now, we've got a nonlinear partial differential equation. And this means, in short, it means we're not going to be able to write the solution down very easily. And with these boundary conditions here, the first condition is a sort of mixed Neumann type boundary condition, which isn't too severe. But the second condition is a Dirichlet condition. That's more standard. But we also have this free boundary condition. So note in this boundary condition, here we have a derivative of h with respect to t. And so this boundary condition here is telling us how the height of the wax layer evolves dependent on the temperature of the solid wax, as well as the temperature in the oil, as well as the temperature TH, where the wax solidifies, as many other things. So this third equation here is our free boundary condition, which tells us how the height of the wax layer evolves. Again, it's, where are we with this? I thought I put that in, sorry. Okay, it's further on. So it's helpful to see sort of a schematic diagram of how this process, how these three PDEs, sorry, this one PDE and 3 boundary conditions match up. But that will come later once we formulate the non-dimensional problem. In other words, once we've simplified the problem to get rid of all the constants, or as many as possible, then we'll go through this. Now, to do this, to simplify the problem, we consider dimensionless variables. So that is, we rescale all of our variables to try and remove as many of the constants as possible from this problem formulation. And so if we do this in the following way, so we write U, which will be our new unknown for the temperature in the, or our dimensionless temperature for the wax, for the solid wax. We write this as so. We also rescale X, that is our variable pointing axis pointing from the pipe wall into the center of the pipe, or the center line of the pipe. We have our rescale our time, and I've already mentioned the time scale TS here. And we rescale our height as well, just by dividing H by the length scale XS. Now it's important here, we take our temperature profile TS, or our scaling for our scaling for our temperature to be dependent on the difference between the temperature at which wax solidifies and the temperature of the coolant jacket. That's probably the main thing. The time scale that I mentioned earlier, so I mentioned time scale when I was talking about how thin the pipe needed to be to make the quasi-steady state approximation. It's just given here. And we note here that in the numerators, we have these TH minus TC things. So namely, they're appearing in U here. And in the denominators, we have these T0 minus TH things here as well. And these are consistent across these. Now, it's worth noting here that from, so these are going to be industrial reports written on this topic. So we can estimate from experimental data what reasonable values for capital TS, XS, TS, or the time scale, the length scale, and the temperature scale can be. I think one of these is a National Physical Society report from Kay and Leiby. The other report's from Schultz, and this was done for Statoil, and it's not published. But this was available to us for this particular study. And these estimate these scales to be along these lines. So, yeah, when we're talking about this wax layer formation here, an important feature is we're talking about it happening over a time scale of, 20 days, a month, that sort of time period. And although I haven't introduced epsilon and k yet, I probably should have put these on another slide. They will be introduced very soon. Now, if you substitute in these dimensionless variables into our boundary value problem, or into our PDE here, and our boundary conditions here, here, and here, what you get is, I've jumped ahead of myself again. I apologize. So we're not finished with our non-dimensionalization of this problem. We still need to consider the wax conductivity. Now, as stressed already, we are considering a non-linear wax conductivity here. And we non-dimensionalize in the following way. So we pick the K subscript WH to be the wax conductivity at temperature TH. So that's the wax conductivity at the melting point, or at the, actually it would be, the melting point in this case, not the solidification point. And then we introduce this function D, essentially to replace this KW here. And D here is just a function of a real variable. So really this is, you can just consider this as a real variable. Now, to get any sort of meaningful analysis, to perform any meaningful analysis here, we need to impose some regularity on the function D. So D here is our dimensionless solid wax conductivity. Why we choose D is perhaps slightly counterintuitive, but we use D to denote this variable because the heat equation is also known as the diffusion equation. And this term, this nonlinear term, would usually be referred to as a diffusion coefficient, or the diffusivity. So it's the heat diffusivity in this case. But yeah, that's why we're calling this function D, because it's to do with the diffusion of heat. And in this case, to simplify our problem in non-dimensional form, we impose that d of 1, that's d evaluated at 1, is equal to 1. And that's just for convenience, really. The second condition, if I can move the zoom bar out of the way so I can see it, this second condition ensures that d is bounded below and above by 2 positive numbers. And so what this does, this condition ensures that heat always diffuses from essentially hot to cold. You can consider it that way. But in a mathematical sense, it also ensures that our partial differential equation is parabolic. So without this type of condition, well, yeah, you can get away from the case where heat moves from hot to cold, and you can get away from the case where the PDE has regularity. So parabolic partial differential equations, be they linear or non-linear, have lots of smoothing properties. So it's quite nice to have them if you have them. Now, a last property of D that we impose is that D is 3 times continuously differentiable. Now, this is much more than one would usually impose, but we do so for a particular reason, which I'll barely mention in this talk, but I will mention it a little bit. It's helpful to have D at least Lipschitz continuous, but or at least C1 with Lipschitz continuous derivative. But we impose a lot more here. Now, for illustrative purposes throughout this presentation, just consider D to look like a sort of logistic function, add 1 to it. So it's 1 plus this 1 hump function. So it just looks like this between 0 and 1. If the value of the constant C is bigger than 0, and it looks like a negative hump if the value of C is less than 0. Of course, we do need to impose that C is not too small to ensure that this condition is satisfied. Namely, there's the lower bound that is bigger than 0. Okay. Now, the next part. So if we now substitute all of our non-dimensional terms into our physical problem for the temperature of the wax, or the solid wax, we obtain this free boundary problem in non-dimensional form. And so this is our initial boundary value problem that we will study from this point that we denote by IBVP. So the PDE has been reduced down to just a simpler looking PDE with only one constant, epsilon. And the only other constant that appears that is a dimensional term, or the non-dimensional term, is this K here. And so epsilon, so that appears in the left boundary condition. That is the boundary between the pipe wall and the solid wax layer. The conditions of the free boundary are now removed from the dimensional term. They have no dimensional terms in them now. I should say here, really, these are really H dash, and this is really a T dash, and this is really an X dash. But we suppress the notation afterwards because we don't want to keep writing dashes after everything. So really, the X and T's here have got dashes next to them because they are the dimensionless variables. But we don't write that usually because it takes too much time and space. Now here, important features of the problem now are going to be prescribed by these particular physical constants, epsilon and K. And epsilon here is given as this relatively simple term, and K is given by this less simple term. But at least you can write these down. Now, estimates for epsilon and K are given here. I gave them slightly too early, but they're given here. So epsilon you can consider roughly as order 10 to the minus 1, and K depends on the Nusselt number, really, of the coolant, but you can estimate it to be, roughly speaking, this. So that there are estimates for these that have arisen from industry, and in particular applications, they can be calculated. Okay, and so that's what so I've called this an initial boundary value problem. That probably looks a little bit curious because I haven't prescribed any initial conditions yet, have I? So here in 1.8, we've got a PDE that's satisfied on our domain where t is bigger than 0. We've prescribed a boundary condition at the left boundary when x is equal to 0. And we've prescribed boundary conditions at the right, at the free boundary. But we haven't actually imposed any initial conditions yet. Okay, so I guess to highlight again, some of the key, so I'll highlight this before we get into the initial conditions. But the two parameters here, epsilon and k, well, in particular k, these will form this will form a key sort of part of the discussion about the physical model that we're going to look at. And so it's worth highlighting here that this k here forms a key part of the qualitative results related to this mathematical model. It occurs to me that I can't see the time on my computer, so I'm going to have to keep track here. Okay, I'm going way too slowly. Okay, so I'll have to speed up a bit. So this is a schematic diagram for the initial boundary value problem. And so we have our left boundary condition here. We have our PDE that's satisfied in the domain here. We have our boundary curve at x is equal to ht here. And we have our right boundary conditions here. Now, to formulate an initial boundary value problem, we need to formulate a condition when t is equal to 0. Well, as you can see, when t is equal to 0, we're contracted onto a single point here because we're starting from the state where there is no wax buildup on the initial boundary or on the pipe wall. So we're starting at t equals 0 with no solid wax on the pipe wall. And so that's what this condition here corresponds to. So this condition here corresponds to starting at time t equals 0 with no wax at this pipe wall. We additionally impose that the temperature uniformly converges to 1 as you approach t equals 0. So this says when you start to evolve, the temperature profile is pretty much just 1. And that stems from this right boundary condition that u is equal to 1 on the right boundary, roughly speaking. And I'll say both these limits here, this convergence here in these limits is uniform. So we impose additionally that this convergence is uniform. Now, I'll note here that this problem was studied by David Needham and Thomas Johansson and Tom Reeve in a publication in 2014. Actually, so the update of this that what I'm talking about now, we conducted this study in 2018, I think, or was it 2019? And we're just getting up, so writing it up and submitting it for publication today. So yeah, it will be submitted for publication today. But yeah, that's where we are. Now, roughly speaking here, what we expect from this boundary value problem is it's going to converge as t evolves to a steady state. So it starts off at t equals 0 with no wax buildup, but it converges to a steady state as t tends to infinity. That's roughly speaking what we expect. So now related steady state for this problem, well, going back, is essentially just a solution to this part of the boundary value problem that is independent of t. And we ignore this part, these initial conditions for the steady state calculation. Now, if you look at the steady state problem, you just remove the time dependency from your partial differential equations or free boundary value problem, and you get this, which is just, which I won't spend much time on. An important detail here is you can pretty much solve this exactly, actually, with a function defined via the inverse function theorem. And you can see this as follows. So if you consider just this top part, so d of u times du by dx, differentiate that with respect to x. If you consider this, well, if you introduce the function f, which is just the integral from 0 to x of your function d, recalling that d here is positive and bounded above and below and nice and smooth, this tells you that f is differentiable, actually a lot of times, four times, and its first derivative is strictly positive. And this means, since the first derivative of f is strictly positive, and it's nice and smooth, therefore, via the inverse function theorem, there exists f inverse. And once you have f inverse, if you just acknowledge that, well, if you evaluate f of u of s of x and differentiate it twice, you'll observe that actually that's the same as just writing this PDE. So actually, that PDE can be reformulated as f of u of s of x is equal to ax plus b. And where you just have to solve for a and b now in a comparable way that we solved the linear case of the heat equation earlier in the talk. And so from this, you can calculate that actually the steady state for your wax layer will have a height f of 1 minus f of k to the power minus 1. And your steady state for u will be f inverse of x plus f of k to the power minus 1. Now, there's a key point here that's probably one of the main points in the talk, which is this. That is, our height hs of our wax layer needs to be positive because that corresponds to our h evolving into the pipe. That can only take place if k here is bigger than 1. If k is less than 1, then that would correspond to h of s being negative, and that would correspond to our height of the wax layer existing, well, outside of the interior of the pipe, or within the pipe wall or the coolant jacket, which is physically not what we're interested in. So a key condition actually that we get from this is that k needs to be greater than 1 to talk about this problem, really. And so this gives you a key feature of when these wax layers will develop. Namely, they will in principle develop when k is less than 1, sorry, greater than 1, and in principle won't develop when k is less than 1. Now, you can plot these steady state profiles here. So for k equals to 2, and for our function d with various parameters c. So we have the function d here is 1 plus, it's our humped function, or negative humped. And so here we plot it for c equal to 3, 2, 1, 0, minus 1, minus 2, and minus 3. And we observe some of the key features here that as the function d increases, so that's with c equals to 3 is the largest value of the functions d. And as you decrease c, your functions go down. Now, as you, for the largest values of c, you have the wax layer reaching a height of hs equals to about 0.75, whereas when c is equal to minus 3, the smallest function d, your height of the wax layer is getting to about x equals to 0.25, and you can see this. This way. Another point to note here is that at the left boundary, the temperature profile of the wax layer here is equal to 1 divided by 2 or 1 divided by k, and this is always the case for the steady states. So similarly, if we plot the steady states when k is equal to 10 with the same function d or functions d, we get similar looking behavior where now at the left boundary we have the profile is equal to 1 divided by k, and again we have the profile heights hs increasing as you increase the diffusivity function, or the function d. Now we get onto the main theorem that we've proved about the initial boundary value problem, IBVP. I've had to skip pretty much all of the details, but summarize the main results. And so you can prove all of these things, or most of these things, all of these things. My statement was correct the first time. So firstly, the existence of a solution to the initial boundary value problem requires that k is greater than 1. I suppose I should say more specifically that we're interested in the cases where the solutions are positive. We need that to be the case. So that's what this first condition means. Now, with k greater than 1, if U and H are solutions to our boundary value problem or initial boundary value problem, that's not the steady state. This is the full boundary value problem now. Then we can say we can say that U, our solution, is bounded between 1 over K and 1. And the way we prove this is via several applications of the weak maximum principle and the strong maximum principle for parabolic partial differential equations. Similarly, and so this thing gives us a bound for U, which we can use for regularity results that will follow, or that we require. Similarly, we can establish that the time derivative of U with respect to t is strictly less than 0. And so this is great because this allows us, with our point 1, to ensure that our functions U of t for fixed values of x, well, U will be decreasing, which tells us that it's got a good chance of having a nice limit as t tends to infinity. And again, we prove this with some neat applications of the weak and strong maximum principles for parabolic partial differential equations. Similarly, we can get bounds on du times du by dx. And this essentially allows us to get an upper bound on how h evolves. So this term du times du by dx is contained in our free boundary condition. And again, we get this via the combination of weak and strong maximum principles and the problem formulation. Additionally, we have this quantity here is less than 0, which again, we obtain this via similar means. And importantly, we know that our free boundary H is bounded above by, well, the steady state of the free boundary and bounded below by 0. And also the gradient of H is bounded as well. As so H is a non-decreasing function. In principle, it's increasing, but at least we can say it's non-decreasing. So those are the qualitative points related to the problem that we can prove and have proved in the paper. Additionally, we have these two final points which say that H converges to the steady state HS from below. I should mention the steady state was unique as well. So the steady states are unique for these problems. And additionally, U converges to the steady state for the temperature profile U from above. And that's because the derivative of U is negative with respect to T. Now, I'll say this point is proved, but this point and the existence parts require probably a little bit more work than we've done, but we've given a justification for the explanation. You can establish these via a similar argument to a paper by Cannon and Hill, combined with the need for improved regularity estimates that you have from classical PDE theory that you can see in Friedman's works or Ladzinskaya or Altsever, Solonikov, and these sort of PDE books. So yeah, that's the main theorem that we can establish, or essentially establish, for the initial boundary value problem. That doesn't tell us, though, everything we want to know. What we'd like to know really is how things converge as t tends to infinity, how fast they converge, and what they look like. And to do this, we now have to switch to doing some non-rigorous mathematics. So some formal but non-rigorous mathematics. And so here we look first at what the solutions to the initial boundary value problem look like for small t. So if we want to look at what the solutions look like for small values of t, well, we know that, well, U is going to converge to 1, and it's going to be that plus some terms that are small with respect to t. H converges to 0 as t tends to 0. So we assume H is roughly big O0, big OT, and X is big OT as well. That's just dependent on H. So now if we rescale our coordinate system to pick X to be equal to little x divided by t and choose that to be order 1, and we now represent little h, our free boundary, in this form, where we have h1, h2 undetermined, and we represent u in our rescaled coordinate system as 1 plus this unknown u1 of x, unknown u2 of x, plus higher order terms. Well, if we substitute these into our initial boundary value problem, actually all we need to do is then match order or match the terms of various orders. And this gives us a representation for h and u. It's not that important what these representations are for the purpose of this talk, but you can see here that h, at least the leading order term, does pick out this feature that k needs to be bigger than 1. So if k was less than 1 here, h would be growing into the negative part of going into the negative direction, which is not what we want. And u is given in this form. I've stated that you don't need to know what these are precisely, but it's more to say that we can compute these. And we'll use these later, actually. Now, the other feature side of this that we want to look at are what these solutions look like as t tends to infinity. So that is, we want to know how the solutions will converge to their steady states. And in a similar way, we know that h is going to converge to its steady states. And so for large values of t, we assume that h is equal to the steady state plus some little o1 term, or a term that decays to 0 as t tends to infinity. Similarly, we suppose that u converges to its steady state plus some little o1 thing. So, well, for large values of t, u is almost equal to its steady state plus this little o1 term. And therefore, we approximate things this way. Now, I'm going to skip all the details of how we do this. By substituting this in, you get an eigenvalue problem to determine sort of the convergence rates. And I'm going to skip all the details of that and just state the results because I'm running out of time. But what this says is as t tends to infinity, u is approximately equal to the steady state plus this term here and this term, which is exponentially decaying as t increases. Similarly, h is equal to its steady state and this exponentially decaying term as t tends to infinity. And so this tells you that actually the convergence to the steady states is happening really quickly for this particular problem. Exponential convergence is about as good as we can expect for this particular problem. Now here, lambda 0 is the first or the largest, sorry, the smallest in magnitude eigenvalue we get from our eigenvalue problem that I've skimmed over. But you can see here that it's given by this. So lambda 0 here is, well, the numerator here is strictly positive because this quantity here is strictly positive. And since epsilon is strictly positive, the denominator is positive too. So we know that for any values of k and epsilon, we have exponential convergence to the steady state, which is good because it means our numerical method will, in principle, work well. So now, we know what the solution looks like for large t, and we know what the solution looks like for small t, or t near to 0. I suppose I'm at the time limit. So Kyriakos, how much would you like me to essentially summarize the main results now, or is it okay to go on for about 5 to 10 minutes?
Actually, if you could summarize in 5 minutes, it will be fine so that we can have some questions. I mean, it's up to you, really. You're the speaker, I mean, but
okay.
Because it's online,
okay, that's fine. Okay, I'll happily stick around for questions afterwards anyway. So
yeah, absolutely.
Yeah, I won't rush. So I'll be done in 5 to 10 minutes. Okay, so the numerical method then, so we know what our solution looks like for t equal small values or t close to 0, and we know what it looks like for t large. We don't know what it looks like in the middle, or in principle, really, how the convergence is resembled. So here we look at a numerical method for determining what the solution actually looks like. We're mostly interested in h here. Now, we have a problem with our numerical method in its initialization, in that when you try and initialize it from a point, and that can cause you some problems. So what we've done here is, in a similar way to the small t asymptotics, we rescale the coordinate system. So we consider a new variable x, which is equal to x little x divided by h of t, and consider a new function v. And so we reformulate our initial boundary value problem in this way for v. So what we do is reformulate the boundary value problem for V in terms of this new variable. And what this does, all it really does is convert our free boundary condition on U into a fixed boundary condition on V. So the difference between V and U here in terms of the boundary value problems is that the domain on the right here is fixed. And so this allows us then to use a numerical method with a nice uniform grid, which we could use a bit more brute force with. So you so the benefit of doing this is you fix the domain. The downside is your PDE gets more complicated. Now, with this PDE, we have a bit of a problem as well in that you can't start this this numerical method from t equals 0 because this PDE is degenerate at t equals 0. And so the numerical method just goes out of control if you try and do this. So actually what we do is instead of starting at the numerical method at t equals 0, we started at t equals delta. And the initial values we take at t equals delta are given by those small t asymptotic estimates for the problem. And so even with this, the numerical method still takes ages to evolve from t equals delta because we choose an explicit finite difference method to do this for the benefit that it's pretty quick to run. The downside is that to keep the method stable, you need the step sizes to be very small. So it takes a while, but the fact is it runs quickly enough so that we can actually compute things. Now, here are some plots of what h of t looks like for fixed values. So we take epsilon to be equal to 0.1 and k to be 0.2. And we consider the same function d that we considered earlier. Then here we can see from these graphs that we start off from t near to 0, and these evolve into their, well, I'll say that the lowest one has evolved to actually reach its steady state, essentially. The lowest 3 have done so. The top ones haven't done so yet. I'll say by t equals 20, they have all flattened out, or all the graphs have converged. But for the purposes of illustrating the difference between them, I've only selected to plot them on up to t equals 3. But yeah, by the time t is equal to 20, all of these graphs have flattened off. And again, you can see that the heights of these curves, so we're plotting y is equal to h of t, or y is equal to height of the wax layer. And as you increase d, you increase not only the height of the wax layer, but also the time taken for this to converge. Similarly, you can see that the gradient at 0 is the same for all of them. And so actually, all the curves are sort of have the same gradient at this initial point. Now, it's worth noting here the difference between the cases for epsilon equals 0.1 and epsilon equal to 1. Now, as you flick back and forth between these, when epsilon is equal to 0.1, you can see, and when epsilon is equal to 1, you can see this changes the convergence speed. So it takes a little bit longer for things to converge when epsilon is equal to 1. They'll still converge to their steady states, but just the time taken will be a little bit longer. And that's reflected in the eigenvalues you have for the convergence rate for h and u to their steady states. Similarly, if we vary k this time in the next, so here we have k equals to 2, in the next one we have k equals to 10. So here the main difference you observe is that the steepness of the initial convergence rate. So when k is equal to 2, things start to evolve a bit slower. When k is equal to 10, the wax layer grows a bit quicker at that initial time and generally. So increasing k will increase the rates of the growth of the wax layer, roughly speaking. And so the main thing we're interested in is h. We actually don't care too much about u, but we can provide surface plots of u without too much difficulty. So this is just a surface plot of u against x and t. So time is evolving along this axis and x is on the right axis. And we can see the height of the wax layer evolving around this top boundary and the temperature profile reaching this steady state temperature profile as t tends to, t is equal to 3 in this case. There's not too much interesting about this really, but you do need to compute u, or these curves, to actually find what h is. So yeah, that's it for this. Now, the last thing, I will get to the end soon. So this is the last bit, which is comparison with experiments. So recall that we have two physical constants in our mathematical model. We have epsilon and k. For the remaining discussion, I'm just going to fix epsilon to be constant and just consider variations in k. So what we have, if we look at k, so if we increase the temperature of the oil, so if we relate this back to our original physical model, if we increase the temperature in the oil, that only appears here. So if we increase the temperature of the oil while keeping everything else fixed, that will decrease this constant k. Similarly, if we decrease the temperature of the coolant, so we make the sea or the coolant jacket colder, so that's here, then this will increase this term and hence increase k. Now, additionally, if we increase the Nusselt number, that is of the oil wax mixture, this will decrease k. So we have our Nusselt number here and here for the, well, just here for the oil wax mixture. And so if this increases, then the constant k will decrease. And so these ideas are strongly connected to some experiments that were done by or conducted by Hoffman and Amundsen. They were published in Energy and Fuels. And after looking at the copyright notices on this, I decided that I probably couldn't include the pictures within this presentation because it's being broadcast or it's going to be made available online. But there are numerous experiments conducted and they largely agree with physical phenomena we predict from the model. But that is, there's a critical temperature Tc above which wax layers do not form. So this is experimentally observed. And in our model, this corresponds to K being less than 1. So this critical temperature corresponds to K being less than 1 in our case, when you don't get wax layer formation. Additionally, as temperature of the coolant decreases below a critical value, the equilibrium height of the wax layer increases. So this corresponds in our model. So to clarify, this is the experimental observation. And in our model, this corresponds to HS increasing as K increases, which is what we observe. Additionally, as the oil temperature, TO, increases, typo there, the equilibrium height of the wax layer decreases. So this was experimentally observed, and this corresponds to HS decreasing as K decreases. Additionally, as the Nusselt number increases, the equilibrium height of the wax layer decreases. This was experimentally observed, and in our model corresponds to HS decreasing as K decreases. I'll say there's good qualitative agreement between H of T that are calculated from the experiments via about 3 or 4 different mechanisms, that and the model. Actually, it's really remarkably similar how well they agree, considering how simple the model is. And I'll say that it's likely that experiments have been conducted by the group in Tulsa as well. Actually, it's certain they have been, but I haven't compared against them yet. I haven't got to this point. So as a final thing, I would just like to thank David Needham and Sophie Mason for really providing the impetus for my involvement in this project, and Ruben Schultz at Statoil for their contribution and in particular their help with relating what we've done to the experiments. And so I would like to thank them at this point and thank the audience for your attention, and yeah, open up the audience to, well, the opportunity for questions. So feel free to ask.
We would like to thank you, John, for this really dense information talk. I forgot to tell you, and I would like to apologize that some people are teaching at 2 o'clock online. That's why we lost around, I would say, 10 people from the audience in the last 10 minutes.
It's fine. It's fine.
It's something that I really forgot. You know, this is
it's being recorded.
Yeah, it's been recorded, and we publicize this through the Math Club and also in the Math Department. So, are there any questions?
Well, can I ask something? I mean,
Of course.
You said this is an industrial report, or let's say, if you are talking to, I assume, an audience of people in the industry, or even I could go as far as say even an audience of people doing physics. I mean, you paid a substantial amount of effort, and apparently it's clear in your theorems about the regularity of the profiles and all these things. Can I assume that people wouldn't really care much more if it was assumed that everything's analytic and finish the job right there?
Well, so probably one thing that's worth mentioning is, by analytic, do you mean C infinity here, or do you mean?
No, that's convergent power series. I mean more than that.
Okay, yeah. So even more, yeah. So in this particular case, it probably wouldn't help you too much. And so saying in the asymptotic approximations, when you're looking at the small time and large time, that's essentially what we're doing. And we're just taking the truncation of the first few terms in a sort of formal power series. For these particular problems, you wouldn't expect the solution actually would be that regular. You'd expect there to be, so in this particular case, because we've put additional regularity on D, we'd get at least 3 spatial derivatives that are continuous. But in general, we wouldn't expect more than that for this particular problem with D as it is prescribed. So if D is a nonlinear but C3 function, we would expect that the solutions would have, the solution U would have 3 spatial derivatives that are continuous, possibly 4, but you wouldn't expect any more than that. And that's the theory wouldn't give you any more. Theory wouldn't give you any more than that. It's quite different to the linear heat equation in that respect.
Do you have any explicit solutions that basically show this? I mean,
no.
Okay, no. I understand. Look, I agree regarding the mathematical viewpoint, but you said that if you present this to an industry, then I think regularity theory is interesting, and of course I am very highly interested also in this. But so my second question, if you do not mind me asking, is: have you ever thought, because you use the Fourier, right, essentially the Fourier law, which is essentially a linear differential equation, have you ever thought about using nonlinear equation, something like a porous medium equation? Which
it's a fair question. So the Fourier law doesn't, I suppose it's in a sense it's kind of a linear law, but it's not it doesn't necessarily give you a linear equation as we've seen here, because it depends on your conductivity.
Right, that's correct.
Linear or nonlinear. But yeah, so it's a fair question to say, well, are there different heat transfer mechanisms you can conduct? So you can consider sort of relativistic heat transfer, which sort of, that's something I've thought about in the past, where at least it limits that opportunity for sort of infinitesimal heat transfer at arbitrarily large distances. So you can get rid of that feature with this sort of relativistic model. But in this case, since we're on the finite domain, it's not so much of a problem, I guess.
Okay.
To answer your question, actually, no. To answer your question very simply, no. I haven't considered using the porous medium equation or that type of mechanism. But yeah, to say that you could, it's not to say that you couldn't. You could potentially do this sort of thing.
No, because you know that there is a very substantial theory of the porous medium equation. Also regularity. There is this guy Vasquez that wrote.
Vasquez, yeah, he wrote a monograph on this. Yeah.
He wrote the huge monograph and so on. And therefore, because again, you have diffusion constants that essentially depend on the parameters. Essentially, it's essentially a nonlinear equation. You may be able to find similar behavior, qualitative behavior in the solutions.
I'd expect that. So theory related to the porous medium equation is going to be related to this, and because of that differential structure in the PDE, where you've got the sort of well, I'll just go back and display it. I guess that's the easy way. So yeah, in this particular part, and this is pretty close to a porous medium equation. It's not.
Yes.
So you'd expect that some of the results would be quite similar. Actually, since this is since essentially the domain we're considering is bounded and everything's being capped above 0, actually probably the behavior for a porous medium type equation wouldn't be that different, because the sort of compact support principles you get for porous medium equations, that's one of the sort of substantial differences you get between these and the more general parabolic things. But you wouldn't actually see these in this case because everything's being kept above 0 anyway. So it's sort of I imagine you might get quite similar features if you instead used a different model than Fourier's law to model the heat transfer mechanism. Another interesting one that is in the literature is sort of for using sort of more particle-based models and looking at sort of thermodynamic models related to how particles interact and how they change state. So there's another way you can model heat transfer in a non-continuum setting. This way, I've seen stuff on this too, and I think one of the critiques of, okay, I don't want to get into critiquing other models at this point, but I know it's stated in the start of our study, which is some of those models sort of have more spurious mechanisms for the wax layer actually reaching its equilibrium height. So sort of you can model things in different ways, and people have done so. Yeah, I think it's a fair question to say, yeah, this is not unique. This is not a unique model for this particular physical process, but it's a relatively simple one that seems to pick out quite a few physical features.
Right.
Yeah.
Right. Of course.
Yeah.
Absolutely. Thank you very much.
That's a good question. Good question.
Thank you, sir.
No problem.
Are
there any other questions?
That's a very good interaction. Any other question about? I will ask a non-mathematical question that might sound stupid, but I know that right now in the Mediterranean we have very big issues about the natural gas, and that might reach even a war. Libya, Greece, Turkey, Egypt. I mean, can this kind of models be kind of modified and include also gas instead of heated oil? I mean, you said something about modification.
I think so. I think so. You'd have to look. So you have to look at the pipeline structure that you're concerned with. So, if the pipelines that are transporting gas don't have this phenomena where they are building up what you call a plaque, like you have like a layer on the outer of the pipe. If this phenomena isn't happening, then there's no need to consider it. And I suppose at higher temperatures, or if you've got things that are in gas state, it's going to take a larger temperature difference to get them to condense down to being in a liquid and even solid state. So with gas things, you probably wouldn't observe this phenomena so much. And actually, even in pipelines where you don't have these sufficient temperature difference between the outer cooling and the inner heated oil in the mixture, you don't observe this phenomena. So actually, if you heat the oil up loads, you won't get this formation. So if you heat the oil up sufficiently much, you won't get wax formation.
Yes.
But you need it to be a sort of right balance of the heat in the oil and the coolant in the exterior to actually observe this phenomena at all.
Yes.
And so you'd say this is a phenomenon observed in particular settings. To say, could you consider it in more general settings? You probably could. I mean, but it's more a case of you consider it where you're seeing the problems. So the problems come from, I guess, Statoil, which is based in Norway, and they study it in Oklahoma in the US, and probably in parts of Canada where they are transporting heated oil in very cold environments.
Very cold, yeah.
So you get these. The problem is pretty informative to see that the people studying these things are people in industry who are have pipelines located in colder parts of the world, and you probably won't observe this phenomena so much in hotter parts of the world. Although you might observe it under sea, but I think it's certainly less likely to be observed in hotter parts of the world. The modeling though could still the modeling could be generalized to this, but probably the physical problem wouldn't appear so much from these regions, I'd guess. I mean, that's just a guess.
Actually, they have found a lot of gas, but they haven't taken it yet. So I think this is research for you in the future. I think.
Then, well, you mentioned depending where the gas is, they have the porous medium equation. Then again, exactly. So if you're doing fracking things, that's if you've got gas that's trapped in rocks, then I guess you're fracking, which is what they've started doing in the UK. And in that case, you would be looking at the porous medium equation because you're looking at trying to force a gas through a porous medium.
Yes.
Now, in that particular setup, actually, you would be looking at that sort of mathematical model to actually get that stuff out. Yeah, there's been a lot of work on that. I guess Vasquez's monograph is the famous mathematical one. I guess there's been a lot of work from industrial and engineering the community in this direction because they they produce gas via these mechanisms across the US, and they've been doing it in the UK. I think for around 10 years now, maybe less than that, but for that sort of period of time. Yeah. But yeah, it's interesting. Yeah, it's an interesting topic that is certainly related.
Nico, you wanted to say something?
No, the only thing that I could say is that because exactly in the Eastern Mediterranean, they are building some pipes. My brother, actually, who's a mechanical engineer, is working in one of them. I think they have a problem with the liquefaction of natural gas, which decreases the efficacy of all these pipes. When they do when they go under the sea. But I guess this is liquefaction. This is not a solid thing. So again,
you can say it's analogous to the process. So here we're looking at a liquid to solid state change. But
right.
yeah, you could in principle look at a gas to liquid exchange as well. And that part of the model you could feed in, and it's gonna be different. You're gonna end up. You could potentially try and model it in a similar way. Say it would be exactly the same is not the case, because we're invoking solid mechanics. We're making approximations in fluid mechanics when we're doing this. The fluid mechanical approximations would have to be different if you're looking at a gas to liquid exchange, as opposed to a liquid to solid exchange. But yeah, in principle, you could try and do the same thing in a sort of comparable way. You could start from the same point and work from there. It's an interesting point, actually. Yeah. So yeah, you could get a conversion from gas to liquid would be. I guess the cleaning mechanism for the liquid would be quite different to the cleaning mechanism for the solid. So cleaning liquid might be easier than cleaning solid. I'm not sure, actually. It depends. And I guess I don't know. Yeah, I haven't considered this, but yeah, the cleaning mechanism as opposed. So the solid state, you need to scrape the wax off the pipeline wall, or potentially heat the pipeline up a lot. Those are your two options. That will be quite different to the liquid case. So the liquid case, you could potentially suck the liquid out by creating a pressure gradient with pipes, or I guess that's the one way you could go about it. But it'll be a different mechanism for removing it. But yeah, it may well be a similar phenomena, but just as a gas-liquid exchange as opposed to a solid-liquid state change. But yeah, so it's a good point. I should look into that at some point.
It was a great pleasure to have you today, John. And virtually, and hopefully next year after Corona, we will have you for a colloquium seminar physically in Kuwait.
I would happily attend in person. So as you may or may not know, so the University of Birmingham has opened a campus in Dubai, and there's probably scope for staff to travel out there as well. So
amazing.
Kuwait's not too far away, so maybe I could combine the two at one point.
Definitely, we will be neighbors. Neighbors. So see you, and greetings to Birmingham, and thank you very much.
It's been lovely seeing you again, and it's been nice seeing you, Nick, and nice seeing you all.
Thank you.
See you, John.
Take care.
Take care.
Bye.